Hi everyone, Evgeny is here and welcome to VSA Online. So we have critical mass and good to go. So today I have a pleasure to host Luke Yi from Stanford University. And without any further delay, Luke, uh, the floor is yours.
All right. Thanks for the introduction and thanks for having me. And today I'm going to present our recent work on early termination for hyperdimensional computing using inferential statistics. This is a joint work done by me, Yifan, Chaiyang, and Sarah. We are from Stanford University. And this work has been published in ASPLOS this year, which is a joint conference of architecture, programming language, and hardware. All right, I'd like to begin my talk with an introduction to emerging hardware technologies. As many of the people here may know, emerging hardware technologies can offer many benefits, such as higher information density, non-volatility, and ultra-low power. And these benefits are not sometimes are better than the conventional technologies that we use today. However, there's a problem with many of the technologies right now. That is, many of them occasionally corrupt speeds, which means they have a higher bit error rate. This may be due to the physical process that they rely on, or like the immature manufacturing process currently, but it may be something that we have to live with if we want to use these kind of devices. And noted by the prior work, HTC is a very suitable computing paradigm for emerging hardware technologies because HTC is naturally error resilient. It has simple operators, is hardware friendly, and also it is very amenable to analysis, even in the presence of hardware errors. And this is interesting and important because then we can reason about how the hardware errors can affect the accuracy of our computation and hopefully have some kind of guarantees, even in presence of the errors. And our group is generally interested in developing software tools for efficiently implement HTC on emerging hardware. Our prior work, HIME, is a static analyzer for HTC. Here, static analysis means that we analyze the programs without running it. So the input for HIME is an HTC specification, which gives the HTC expressions that we want to compute, and also the accuracy constraints, and also a hardware specification, which gives the profiling the error rates of different hardware components. And HIME would do the analytical analysis based on the specifications and find the optimal hypervector size and the thresholds that we use in the computation. Here, optimal means that we would want to achieve the lowest resource usage while while meeting the accuracy constraints. And here, HIME can be applied to a range of classical tasks such as database, analogy, and knowledge graph. However, because HIME is analytical, it also has certain limitations due to the assumptions HIME makes. Basically, HIME makes assumptions about the independence, and also HIME assumes only using the symbolic base vectors. You generate the hypervectors randomly for different symbols, but HIME didn't allow using numeric or level-based hypervectors, as is often used to represent numbers. And the independence assumptions here, the independence is not about the different elements in one vector, but rather the symbols that you use in one expression or bundle. So one example would be that A binds B plus A binds C plus B binds C. This simple expression would break the assumption made by HIME. However, these expressions and the use of numeric hypervectors are quite used often in tasks as machine learning. Also, HIME is a static analyzer. That means HIME needs to analyze all the possible scenarios and often the worst case. So it can be overly conservative sometimes, and also it does not take each input characteristic into account. So this motivates us to for this work. And the problem here we want to solve is to dynamically optimize HDC. That means we optimize the computation while we're computing through individual inputs. And this technique can be applied to a wider range of tasks. But in this talk, we'll focus on the ML classification because it is a representative and quite useful complex tasks. So since this room is familiar with HDC, I'll give a one-slide review of how the principled HDC is used for the ML classification problem. So in the principled HDC, we have an encoder that encodes an input, which can be image, sentence, time series data, into a hypervector. And the encoder will use randomly generated base vectors to encode automatic symbols and values. For values, we may use level-based as well. And the element-wise HG operators, bind, bundle, and permute, are used to compose these base hypervectors to get the final hypervector representation. And each of the class is represented by a class hypervector. And in the principled HDC, the class hypervector is the simple bundling of all the hypervectors of the training samples. And during the inference, we encode each input, and then we calculate the encoded hypervector's distance to all the class hypervectors. And the class with the lowest distance is the classification result. An interesting property of the principled HDC is that it has IID hypervectors. And there are several reasons for that. First, the base hypervectors are IID by design. And the HT operators are element-wise. So there's no interaction between different elements. And the training is just a simple bundling. Again, no interaction between the elements. So here, one caveat is that the permutation operation may sometimes introduce slight correlations between the elements. But as noted by the prior work, permutation can be seen as a type of binding, and sometimes is computationally equivalent by creating a new hypervector using binding with another random hypervector. So we'll leave that detail and continue with the current the IID assumption. And this connects well to the fully distributed property that have been proposed by Penty back in 1997. Which means that the information is distributed holographically and superposed in the vector, and each hypervector element is equally important or unimportant. And this property enables us to do dynamic optimization in a quite direct way. That is, we can just compute fewer dimensions of the hypervectors to make a classification. And because each dimension is equally important or unimportant, so leaving some of the dimensions will not result in a large corruption in the information encoded. And we can use more dimensions for harder inputs and fewer for simpler inputs. Since the inference computational cost is roughly proportional to the number of hypervector dimensions we use, if we can find a good confidence metric that tells us when to stop, then we can potentially save the compute without much loss of the accuracy. Prior work has explored this idea quite a bit and designed various heuristics for the early termination based on the partial distances of the current hypervectors that we have computed. Some use a static threshold for the absolute smallest distance, and some set a static threshold for relative distance margin. That is, you compare the smallest distance to the second smallest distance. And if the difference is large enough, then you are confident with the result. And some work also set a distance threshold for each class, which is more detailed at the finer granularity. However, these heuristics do not exploit the fully distributed property of HTC, and it has no accuracy guarantees. It can be potentially too aggressive or conservative unstably depending on the data they see. And also, their thresholds are static, set before any inference happens. And during the inference, they don't take the data into account. And they need extensive tuning to get these good thresholds. To address these issues, we present Omen, a dynamic early termination engine using inferential statistics. And Omen is based on the HDC's fully distributed property, and because of that, Omen can have guarantees on the accuracy loss. And Omen works with a user-defined confidence level, we call it alpha, that sets an upper bound the user is willing to suffer from on the accuracy loss. Omen is agnostic of the training algorithm, the HDC variance, different encoders, datasets, and even the hardware error levels. So can be directly deployable. And Omen is based on our statistical interpretations of the inference in the HDC models. So remember that in the principled HDC, each hypervector element is IID. So we can see different elements in one hypervector as different samples from the same distribution. And when we compute the distances, essentially we are computing the element-wise distance elements and then average them to get a final distance. Take the Hamming distance, for example. We computed the XOR of the corresponding elements in two vectors. And in the end, we average the XORs. So we can see, we can view that there is a distance vector where each element is the ith element is the distance of the ith element of the first vector and the ith element of the second vector, and they form a vector. And because the two vectors that we want to compute distances are IID, this distance vector is also IID, and like they are sampled from some distance distribution, which we don't know, but there's an underlying distribution. So when we compute the distances, we are essentially summing up the distance elements and average them as approximation for the expected distance. So in the inference, when we compare different distances, what we are doing is actually comparing the approximations of the expected distance. And ideally, we want to classify the input to the class with the smallest expected distances. So in this sense, we want to use as many dimensions as possible. However, the problem is that with more dimensions, you also spend more time, more resource on the computation. So is there a way that we can use as few dimensions as possible while drawing a robust conclusion? This might sound familiar because it is a problem that are encountered in other scenarios. And we borrowed ideas from the manufacturing quality control problem. In manufacturing, we want to have certain quality guarantees on the products. And ideally, we want to use as many samples as possible so that our result is robust, is statistically significant. However, the samples are expensive to get and test, and we don't want to waste so many products, right? So the statistical tests are used by the manufacturing people to determine the number of samples that are needed to get a robust conclusion. So the way they do that is that they sample and sample until that the results are statistically significant. In their algorithm, this means that the results pass a statistical test. So borrowing that idea, we can see there's an analogy between the product sample and the hypervector dimension. So we can sample or like compute more dimensions until the results are statistically significant. I'll use a running example to illustrate how this works and how our Omen engine works. And the example is a sentence language classification. So the classifier would get a sentence as input and inference which language this sentence is from. And we will use the trigram-based text encoder, which is quite a standard encoder in the HDC community. And for the inference, we would encode the inputs and then calculate the distance of the encoded hypervector to 5 languages, class hypervectors, and classify the input to the winning class with the smallest distance. And this is an illustration of how OMA works. And I'll walk through different components of this figure step by step. So the user will set a set of termination points. And here the termination points are around 1,000, 2,000. And this can be user-defined, and it can be just one termination point. For example, if the user just want to check it once, and if not confident, then compute to the end. Or it can be a fixed interval, like check every 1,000 dimensions. And for each at each termination point, Omen would conduct a statistical test and to assess the confidence we have with the current result. If the test fails, then we say, okay, we are not confident right now, and we want to compute more samples to make sure. If the test passes, then we are confident and terminate early and return the current result. And the statistical test use a parameter called alpha, as we mentioned before, and is the accuracy loss upper bound provided by the user. And here we use alpha equals 0.05. Okay, so now let me dive into the statistical test. What do I do here? So with the alpha, at the time when we reach a termination point, we look at the current distances that we have. And there is a, so based on the current distances, there is a winning class with the smallest distance. So let's say the current winning class is Dutch. That is, Dutch has the smallest distance based on just the first around 1,000 dimensions. But we want to make sure that the expected distance to Dutch is indeed the smallest because we are seeing only the samples. We want to make sure the expected distance also have this property. So we will set a null hypothesis for each language that the expected distance of Dutch is bigger than the expected distance of the other language. And this is because in the statistical test, we set the null hypothesis that is contrary to what we want to prove or what we want to conclude. And based on the null hypothesis, we compute the p-value. That we see this observation if the null hypothesis is true. And if the p-value is smaller than alpha, then we conclude that we can safely reject the null hypothesis without suffering from much error rates, and conclude that the expected distance of Dutch is indeed smaller than this language. And in this way, the probability that we make a mistake when the null hypothesis is true is smaller than alpha. And we do this test for English, for French, for Italian, for German, 4 languages. However, one problem arises when we do this 4 times or multiple times when there are multiple classes. And this problem is called the multiple comparison problem, where if each test has a failure rate of alpha, if we do this multiple times, the error rate is not bounded by alpha, but alpha times the number of tests. But we want essentially that the global failure rate, that is the error rate that any of the tests fail, is bounded by alpha. And luckily, there is a way called home buffered method that can adjust each test rejection bound to account for this issue. What the Hom-Bonfori method does essentially is that we will first compute the p-value for individual tests. So we have 4 tests, so we have 4 p-values. And then we sort these p-values in descending order from the largest to the smallest. And based on the rank, if a test is ranked J, then we compare the p-value to alpha over J. So the first p-value is compared to alpha, and the second p-value is compared to alpha over 2, and so on and so forth. And if any of the test fails, if any of the p-value is greater than or equal to the bound, then the whole test fails. And by union bound, we can prove that the error bound that any of the test fails is alpha. And so in this example, the first test fails because the first p-value is slightly greater than 0.5 or 0.05. So we will continue execution. And for the implementation of Omen, for the p-value computation, we use the Walls test. And here, this symbol means the probability density function of the normal function, a normal distribution, and the Zn here is the partial distances. That is the distance, the sum of the distance elements for the n elements that we have computed. And the CDN here is the squared differences between the distances. And we compute this because we do a paired comparison. And this is to account for the correlations between different distances. As you may have thought about this, the distances are not independent because closer to one class may mean more distant to the other classes. This is computationally intensive to compute, but we can rewrite the inequalities we want to test, and we get this expression. And this is much more computationally efficient because the right-hand side are just some constants that we can pre-compute. And here J is the rank, so J is in the order of the number of classes. We can pre-compute for each class and store in the memory. And the Z and CD, the partial distance or partial square distance differences, can be incrementally updated when the new dimensions are computed. The CD term may be a bit computationally intensive because it scales quadratically with the number of classes, but it can also be pre-computed for the binary scatter code. Okay, so now let's talk about the accuracy guarantees of Omen, what that means and why that holds. I'll first break down the accuracy for the normal unoptimized HGC inference. So there are samples that are correctly classified and there are samples that are misclassified. And we further break down the misclassified ones due to for their reasons to be misclassified on. The first reason is the model limitation, by which we mean that the expected distance mismatches the true label. That is, if the correct class is Dutch, but the expected distance to Dutch is actually greater than the other class distances. And for this type of error, there's nothing much you can do unless tune the training algorithms or strengthen the training data you train on. But even if you compute infinite number of dimensions, you still get a misclassification. And the second type of error is approximation error, where the misclassification is due to the small hypervector length that we use. And if we were to use more dimensions, we may potentially correctly classify these samples. And Omen could potentially add on some misclassification in the originally correctly classified ones because Omen sometimes terminates even earlier, so that the approximation to the expected distance is even less accurate. However, this type of misclassification corresponds to the type 1 error in the statistical test, where you reject the null hypothesis, but the null hypothesis is true. And the error rate of the type 1 error is bounded by the confidence level alpha that we use. So in summary, the misclassifications that Oman creates is bounded by alpha. So the accuracy loss compared to the unoptimized baseline is bounded by alpha. Okay, so far we've demonstrated how Oman works for the principled HEC, but now I'll show how Oman works also for the learning-based HEC. And I'll tell you what that means just in a second. So far we've applied Oman to the principled HEC. As we mentioned, the training is a simple bundle, and the hypervector elements are IID. The only assumption that Oman makes when doing the test is that the data or the samples that dimensions satisfy the central limit theorem, the CLT. And when the hypervector elements are IID, they naturally satisfy the CLT. So far, so good. The theory works out, and we have a sound upper bound. A range of HTC training algorithms have been developed that is more sophisticated and can boost up the classification accuracy. And these training algorithms, they update the hypervectors based on the hypervector distances using heuristics or optimization methods. And they can learn a more compressed hypervector representations in this way. And we are interested in applying Omen to these learning-based hypervector training algorithms because they can achieve higher accuracy with much fewer dimensions. So take an example in here in the MNIST dataset. The principled HTC using the simple bundle as the trainer would achieve around 80% accuracy with a dimension of around 10,000. And if you use a distance-based training method, that is, you update the hypervectors based on the distances using the heuristics. And so the class hypervectors is not a simple bundle, but a weighted bundle. If you do that, then the accuracy can be boosted up to around 85 for binary scatter code and around 97 for the real-valued hypervector. And if we use optimization-based methods, that is, if we do gradient descent to optimize the hypervector representations, then we can get around 97 or 98 accuracy with just 5,000 or even around 256 dimensions, which is quite a significant drop in the number of dimensions, but the accuracy is even higher. Okay, this learning-based HGC training algorithm are great. However, they do create some issues for analyzing them because they may have non-IID hypervectors. And the reason is that they use distances, right, to update the hypervectors. But the distances are aggregate information of all the elements in two vectors, right? So they create a correlation between these elements and thus breaking the IID assumption that we had before. So how do we address this? Now we want to ask a question. Does this learning-based HGC algorithm actually break the fully distributed property of HGC? Or rather, because we know that they are not IID, the question we want to ask is that, is the fully distributed property equivalent to IID? So it's hard to just analyze them and say, oh, this is fully distributed and this is not. So we need to find some kind of metric or evidence, right? So we use error resiliency as a test for the fully distributed property because HTC's error resiliency has been attributed to the fully distributed property because intuitively, corrupting some elements in a fully distributed representation would not corrupt the encoded information by much. And that's the source of the error resiliency, as people have has believed. So if we can check whether the learning-based HEC is less or more or even equally error resilient as the principled HEC, we may have some insight of whether they are fully distributed or not. And surprisingly, a prior work has found that the gradient descent-based training algorithm for HTC preserves the error resiliency. So in this figure, we have three lines that corresponds to three training algorithms. The baseline, the blue line here, is the principled HTC using the simple bundle as the training algorithm. And the red line here is the training algorithm called online HT, which uses heuristics to do the weighted bundle of different hypervectors. And the orange line here is the technique proposed by this paper, which uses the gradient descent to optimize the hypervector representations. And we can see that with the increasing error rate, the accuracy trend is kind of similar for all three of the techniques. So their error resiliency doesn't really differ much. So this got us thinking, maybe IID is a too strong condition for the fully distributed property. And we take a step back and revisit the fully distributed property. And for the first point, that the information should be distributed holographically and superposed. And we think that this may be interpreted statistically as that each hypervector element should be identically distributed because the information as a whole is encoded in just one distribution, and each element is a piece from the same distribution. And for the second point, each hypervector element is equally important or unimportant. And for this, maybe we need to find something that is weaker than IID. But it's not that we can just use identically distributed to for this property because it does not capture the symmetry between different elements. So we want something that's in between IID and identically distributed, and also it should hold for these learned hypervectors. And through some literature research, we found that there is a statistical property called exchangeability that can serve as a good middle ground. And exchangeability, the definition is shown here. And it basically means that permuting the different elements does not change their joint distribution. So their indices, the indices of the variables are immaterial in this in their joint distribution. And we will prove that exchangeability implies identically distributed and also a symmetry between different hypervector elements. We'll first prove that IID can indeed imply exchangeability. That is, exchangeability is weaker than IID. And this proof is quite straightforward. If we assume IID, then their joint distribution is just the product of their marginal distributions. And we can change the order of the products without changing the result. So changing the left-hand side would result the same right-hand side. So by definition, they are also the W1, W2 to Wn are also exchangeable. But the reverse is not true. And a simple example is that two variables, x1, x2, they are both Bernoulli 0.5, but x2 is equal to 1 minus x1. In this example, these two are exchangeable, but clearly they are not independent. We can also prove that exchangeability would imply identically distributed. That is, exchangeability is stronger, and the proof is also quite straightforward. We first write out the marginal distribution of the W1 by integrating over other variables, and then because of the exchangeability, we can change the index x with W2 without changing the value of the joint probability density function. And now we switch the variable name by changing the name of W1 to W2. And that gives us the PW2x, which is the W2's marginal distribution. So now we have proved that exchangeability is in between IID and identically distributed. And we also want to prove that the training algorithm would indeed create exchangeable hypervectors. And for that, we will only need to prove that each training step is an exchangeability preserving transformation, because the hypervector elements are initialized to be RID and exchangeable. If we can prove the training step is exchangeability preserving, then the final hypervector has exchangeable elements. So before I dive into the proof, we'll introduce some primitives. We'll first define W to be length n hypervector. Length n vector, just a vector. And the pi is a permutation from the integer set 1, 2, 3, 4, n to the integer set to n. And we put the permutation before a vector to mean that we permute this vector by the permutation. And if a function is symmetric, we mean that this function, so first the input of this function should be a length-7 vector W, and the output can be anything. But symmetric function means that permuting the input doesn't change the output. An element-wise function is a function that takes into input a length-n vector and also output a length-n vector. And a function is called element-wise if we permuting the input has the same effect as permuting the output. Okay, and now we'll use this theorem from prior work to prove the exchangeability preserving of the training algorithms. This theorem basically says that if for any given permutation pi1 that applied on the transformed input, it has the same effect as applying a permutation in the input before the transformation. And actually, we'll prove even a stronger version of this. That is, for any pi applied on the transformed W, it is the same as if we just apply the pi in the input. And we will also define what W means in our proof. And here, we basically arrange the hypervectors in a matrix where each row is a hypervector. Here, the hypervectors have the base hypervectors and the class hypervectors. So they are each hypervector is a row, and the elements of the same index is in the same column. And we would call a column in different, so the elements of the same index in different hypervectors as a one random variable Wi. So the W vector is the whole matrix, and each element of the W vector is a column in this HEC matrix. Now we're ready to introduce and prove the exchangeability preserving property for different algorithms. The first type of algorithm use weights that based on distances to update the hypervectors. One example is called online HD, and in this example, if one input is misclassified, then the correct hypervector would be added by the training hypervector multiplied by the distance, and the misclassified class would be deducted by this the distance times the training hypervector, and this is to avoid model saturation, because if you take the distance into account, then the higher the distance, that means you need to that means the training input is less representative currently in the class, so we want to bring them more together. So this is intuition, and here to put into our context, the class hypervector here is part of the W that we defined. And here, the distances can be generalized to be a weight that is a function of W, which has the encoder, the base vectors, and the class vectors, and also the input T. And the hypervector encoding is also a function on W and T. So the transformation looks at this. So G is the transformation. And we can write out the derivation to get the theorem that we want to prove. So the first step is to distribute permutation over the vector additions, because addition is an element-wise vector operation. And then we can put pi into the weight function, because the weights are based on the distances which are symmetric about W. So putting into a permutation does not change the output. And the encoder is element-wise because the HD operators are element-wise, so we can also move pi into the encoder function. And this will just directly give us the G pi W, which means permuting the output is the same as permuting the input. And the other type of training algorithm is optimization-based using gradient descent or methods alike. And some algorithms randomly generate hypervectors and learn the class hypervectors, and some would jointly learn the base and class hypervectors. And for this type of algorithm, it's also straightforward to prove that they are exchangeability preserving. And here, the first step is also just from the first line to the second line is also distributing the permutation over the vector subtraction. And from the second line to the third line, we are assuming that the gradient is an element-wise function about W, and now we can prove why. So in the HDC, the loss function is symmetric about W, the base vectors and the class vectors, because the loss function is based on the distances, and the distances are symmetric about W. And we can prove that if the loss function is symmetric about W, then the gradient is an element-wise about W. And this is the proof. And the proof basically write out the gradient definition and change the variable index and then get the result. So in summary, we have established that exchangeability is a middle ground between IID and identically distributed property, and also the learned hypervectors are indeed exchangeable. Now we can discuss how Omen can be applied to these learning-based hypervectors. So as I mentioned, Omen's test statistics assume central limit theorem on the samples, but in which conditions does CLT apply to exchangeable variables is still an open question. And we know that for sure by some theorem that the infinite sequence of exchangeable variables are conditional IID in which CLT can apply. But the hypervectors are finite, so there are finite elements and may not be conditionally IID. But they can be approximated by a subsequence of an infinite sequence. We found this result, but the bound shown in this approximation is quite loose, and we are not 100% certain whether Omen can be applied soundly to these exchangeable hypervectors. But in our evaluation, we found that in practice, Omen can work, and the accuracy loss is bounded by the alpha. So now, since we are running out of time, I'll briefly show the evaluation results. We found that Omen delivers better termination results than heuristics, and also Omen's accuracy loss bound holds in all the benchmarks. We have 3 training algorithms featuring the heuristic descent space and also the gradient descent-based training algorithms, and 2 HDC variants, the binary spatter code, and the real-valued version of map. And we have 4 datasets. We measure our runtimes on a microcontroller with 1 ARM Cortex M33 core, 2 megabytes of flash memory, and around 800 kilobytes SRAM when possible, and only with 2 for 2 training algorithms, because their hypervectors are too large, they cannot fit in an MCU. So for them, we compute on a laptop. And here is the results we get for the unoptimized inference. And we would compare Omen with 3 alpha levels from 1%, 5% to 10%, featuring from the most conservative to the most aggressive modes. And we compare them to the heuristic early terminations, and also a static cutoff baseline. So the static cutoff baseline basically uses only n dimensions for every input, where n is the average number of dimensions used by alpha, Omen alpha equals 5%. And this is to prove or show that Omen is better than static threshold. And for the matrix, we would compare the accuracy loss of different baselines to the unoptimized baseline, and also the speed up compared to the unoptimized baseline. And here is one figure showing the results on a UCI here, the human recognition dataset. And I'll show you how to read this figure step by step. So first, the x-axis is the speed up over the unoptimized baseline, and the y-axis is the accuracy loss. And we reverse the y-axis so that the points the up the better, and also more to the right the better. The colors represent different benchmarks, so we would only compare the points of the same colors. And the shapes represent the baselines. And Omen is in circle. And we connect the Omen with different Omen points for alpha equals 5, 1, 5, 10% by lines. And to show which baselines are the best, we would use orange box to represent the Pareto frontier for each benchmark. And we can see that in this figure, almost all the Omen points are on the Pareto frontier. Only one exception, and this one is because it is dominated by the other Omen points. And this holds for all the other 3 datasets as well. We also find that Omen's accuracy loss is consistently bounded by alpha. And here, different colors mean different alpha values. And we use horizontal lines of the same color to indicate the accuracy bound these points should observe. And we found that all the yellow points are above the yellow line, all the red points are above the red line, and all the purple points are above the purple lines. And we also conclude that we also found that Omen incurs small overhead because the major overhead comes from the encoding, and Omen can cut a major part of it. And the statistical test overhead is negligible compared to the encoder overhead. We also confirm that Omen works in presence of the hardware errors out of the box without any tuning. And here we measure the accuracy with the hardware error rate of 2% and 13%, which are the real hardware error rates we collected from resistive RAM emerging hardware technology. And we found that Omen still performs the best compared to the heuristics, and also Omen is consistently above the accuracy loss bound. So in summary, we presented Omen, the first HTC dynamic optimizer with accuracy guarantees. Omen is agnostic to the training algorithm hardware platform, and it provides fine grain per input early termination, and it offers better accuracy performance trade-off. We also identify exchangeability as a statistical interpretation of fully distributed property. And for the future work, we envision that we can design more dynamic optimizations, for example, using other statistical tests or more aggressive but maybe more unsound optimizations based on Omen. And we can apply Omen to scenarios where most inputs are easy, such as always on device, where Omen should give us a good performance boost up. And thank you, and I'm happy to answer any questions.
Thank you, Luke, for the great presentation. So lots of interesting information. So let's see if we have questions in the audience. Please unmute your
Thank you.
microphones and speak up. Let me see.
I have a question.
Yes.
If that's okay that I start.
Yeah.
I have my camera. Yeah. Thanks for the presentation, Luke.
Thank you.
I'm thinking about, you mentioned that it's kind of hardware platform agnostic, and I think I see no problems with that, but I'm still curious, do you think there are still some characteristics of the hardware that would be more amenable to using this method? Like what I'm thinking about, right? If, let's say, you use some kind of time multiplexing or time folding, so then your hardware is more like sequential. Then it's very natural that you do the chunk of computations, you do the estimates, and before going for the next chunk, then it makes very much sense that you check your sort of your method and decide whether to go for the next chunk or not. But for example, if it's like in memory hardware, right? The computations are done anyway, right? You wouldn't save much, or you probably cannot even do so, maybe unless you have several chips, and maybe you can do one chip and then you can decide, okay, I don't go to another chip. But I'm thinking that there might be some also sort of kind of taxonomy of the types of hardware that would be more amenable for this method.
Yeah. That's a great question. Yeah, I think so right, you're right that like for example, you can have different granularities on that's dependent on the hardware. Like for example, different chips and and also one scenario that we were thinking of is like for example in memory computation where like you may have to limit the hypervector length you compute each time to limit the noise level. So like here you also want to like partition the hypervector to chunks and compute each chunk by chunk. And so yeah, that's configurable for our algorithm. So I was yeah for this one, yeah, I think is it true that we may have like that different termination points basically to make Omen works with these different hardware platforms. Yeah.
Thanks. Yeah,
Yeah,
thanks for
thank
the
you.
elaborations.
Look, I have a question on my own. I'm wondering, well, when introducing this kind of progressive precision approach, so you mentioned that you kind of operate on chunks, say of 1,000. So your cutoff lengths are you mentioned it was like 1,000 and 2,000, something like that.
Right.
I wonder if you kind of tried with even smaller chunks, like maybe 64 bits or 100 bits, so that it could fit like even conventional embedded hardware. So does it make
Yeah,
sense?
that's a great question. Actually, in our evaluation, we use a chunks that is around 64 for some benchmarks and 4 for other benchmarks. And we use 4 for this one with the smallest size because 64 would be too large. But we can see that even with smaller, like this is fixed interval, every 64 size dimensions, we do a test. And this still works quite well. So yeah, I think Omen can works with smaller chunks as well.
Okay, good. And then I have another question, just to increase my understanding. I mean, when you compute p-value, I mean, in this form, I wonder, I mean, does it make sense to think about kind of hardware-friendly softmax, like
Mm,
more kind of traditional for machine learning way of computing probabilities?
mm. Yeah, I see the question. Yeah, I mean that could make sense, but yeah, in this work we try to get the p-value to represent. Sorry, let me go back to the slide really quick. Yeah, we want to let the accuracy loss upper bounded by the alpha. So we want the p-value to be to represent like a probability or the upper bound of a probability of making a mistake. And I
Yeah.
think for the softmax, yeah, it may not carry that information. Yeah, but I think in general this is interesting to explore because I think softmax also has certain statistical interpretations, like likelihood or something. Yeah, but yeah, I think that would be interesting to explore.
Good. Okay, so maybe I should keep quiet for a while, and see whether there are other questions, please. So, more questions from the audience?
Thank you. They are all great questions.
Yeah. Okay. So let me check the very last time. Well, if there are no more questions, so you always can ask online. So Dennis, you are unmuted. You want to ask something?
I'm not entirely sure, but
Yeah.
I have kind of simple question. Since you already
Sure.
mentioned that this is published, right?
Yeah, yeah.
Are you now kind of like what are you doing now? Like are you going more towards like making more theoretical methods, or are you, as you mentioned, like trying now to build some hardware, use and demonstrate that on the hardware?
I see. Yeah, I think so our group is a software, like more on software or programming language, and also I'm more about like analyzing the computing paradigm. And yeah, but I would want to like maybe incorporate some like hardware data, for example, to analyze this data. But more on the software level, I'm not a hardware person that can build the hardware. But we work with other hardware groups that may potentially build like HTC accelerators and things alike. Yeah.
Nice. Yeah, thanks.
Yeah, to add to that, we work with people that work in Philip Wang's group, and also Chaeyoung, who's also in the call, is in Zarina's group. She also works in embedded systems, and so those people tend to try to carry out these ideas to the hardware side.
Right. Yeah, and I guess they were publishing for some years ago. I think Penty turned himself. I think there was some project right between Berkeley and Stanford at some point.
Yeah, I was wondering. See, I use the term fully distributed property, and you've used that in your talk. But is there really any difference? I mean, Tony played holographic reduced representation. That predates. But is there really any difference if you think of holographic representation and fully distributed representation? Are they the same thing?
Yeah, I think in my understanding, like holographic is like one condition of fully distributed property, because like it says that the information should be superposed but not like each element is equally important or unimportant. But that's just my view. Like I'm not like the audience should know better than me, but yeah, that's my understanding.
I have a question. I even maybe it's more a question to Sarah, but I mean, look, it's I mean to the same question is to the same extent the question is to you as well. But and it's very high level question. So you contribute to hardware embedded systems community. So what are the trends there? So how people what people think about HDC? I mean, what is a kind of reaction on your contributions within these communities?
I mean, I think they're pretty well received, usually. I mean, and there's also, I mean, in general, there's been a lot of like HDC work, especially in recent years. Like I was serving on the DAC TPC, and we had a lot of HDC papers. So I think there's some excitement like on the embedded systems side. But I also, I mean, okay. Trying to think of how much I should say.
Okay, good. But then, well, sorry, now I'm changing topic. I had one technical question again to increase my understanding. Look, you mentioned, I mean, when talking about evaluation on different computing platforms, so you somehow mentioned, I mean, you had some memory problems or something. I mean, with one of these ARM architectures, I'm thinking if you do this kind of progressive computations, can you think of kind of cache-like mechanism? So if so that you retrieve chunks, sequentially when needed, so you don't need to keep all. So where this memory issue comes from, if you can principle kind of cache continuously needed chunks and work on smaller vectors.
Yeah, that's a great question. That's a great question. I think for our evaluation, some benchmarks cannot fit not because of the memory, but all because of the flash, like the whole like disk or like the flash memory cannot fit in the class hypervectors, like the model. Yeah, you can like sequentially sorry.
Yeah, it's like you literally cannot store the model in the hardware.
Yeah.
This is not an HDC specific issue. Like a lot of classic models like have this issue in spades. So like ML models, neural nets and stuff.
Yeah. Okay, I got it.
Yeah.
Okay, then that was it for me. Jill, you wanted to ask something?
Yeah. One of the trade-offs is resistive memory, and the memory has an error rate, and the error rate has to be matched out. The other thing is that the hypervectors have to be the solid memory, in other words, the long-term memory, and that implies that you have to have a memory that has a very low error rate. And so there's a lot of trade-offs that are basically have to be looked at before there's a decision, let's say, by making a standard of a particular memory. Right now, there's one memory that has a pretty good look, and that's the ferroelectric. And ferroelectric has about a 10-year retention.
And the bit error rates for ferroelectric, is that on the same order as DRAM, or is it closer to resistive RAM? I mean, I'm aware that there's a whole cornucopia of memory technologies that people are constantly investigating.
From our point of view, it's pretty sure that that's what's going to be used right now. We had the one memory manufacturer, Nantero, that had the carbon 300-year memory, and they went out of business, and so we don't know what's happened to any of those patents. So it's lying in reduction. So the only one is ferroelectric.
And do you happen to remember
Micron
the error rates for ferroelectric for FERAM? Because first we just take a bit error rate, so
Yeah, it's got to be somewheres in the 10 to the minus 15 or so.
Okay, so
error
it's on
rates.
par with DRAM in that case.
Yeah, it's on the same level as DRAM. Whether or not there wasn't at IEDM, the last meeting here, there wasn't any real news since a year ago when Micron announced their
Okay, well in that case,
ferroelectric memory. So
air resilience is not as important a property for that device.
Well,
right?
on top of this is whether or not they're going to also additionally apply in-memory compute.
Yeah.
So that's quite a few balls to juggle, and we're not sure how that's all going to end up. So we'll see.
Yeah, well, I suppose with these, the air resilience property really just gives you more slack in your design, right? So even if your devices are reliable, it could be hard to get the analog circuits to behave in a way where you reliably get the right value, right? So you just get more slack.
Yeah. Well, we're talking about something that's actually far, far distant in the big picture of things. But now that we see Microsoft adopting the like of HTC in
oh, they are?
We ran across this a couple of weeks ago, maybe a week ago, I don't know. But it kind of amazed us that we could talk to their version, let me see, of, let's see, I got that in here. Wait, one. Yeah, I've still got it. Of Copilot, and you can talk to Copilot in HTC. I don't know if you tried this, but it's fascinating to mess around with. I think everybody should take a look at Copilot and talk to it in HTC. It seems to know a lot, which surprised us, actually, that you could actually do a financial calculation and do a prediction with HTC. So I don't want you all running off trying it, but evidently it's it's on queue at Microsoft. So I don't know what that's going to do now. All right, if I can go to Copilot and do calculations for a financial prediction, how does that change the market? And I think it changes it a lot, actually, because I don't think you have to be university trained to actually get an answer that's usable. So we'll have to see how that works out. It's a big enough change to for I think academia to take a look at the effects that it's going to have on how we handle the future of VSA HDC. That's about it.
Yeah, thanks, Jill, for this hint. I definitely will look over.
You're welcome.
So let's see. Last chance to for a question from the audience. Let me check. If not, then probably we have to wrap up for today and let European audience go to bed safely. And I just want to remind you that the next webinar will happen in 2 weeks' time. So we will have 2 shorter talks from Sapienza University in Rome. So you're more than welcome to attend. I will send you a calendar invite shortly. So thank you all for coming and attending today. So, and see you in 2 weeks from now.
Thank you.
Bye-bye.
Bye.